Hello everyone, welcome to the 11th tutorial session of problem solving through programming in C. This is a SWAYAM course floated by Professor Anupam Basu from Department of CSE IIT Kharagpur, and I am Siddhant. I am one of the 3 TAs who are in charge of taking this tutorial sessions, where we will discuss a few questions regarding the corresponding week's lectures, and these questions might be helpful for you in solving the assignments and the final exam. So in this tutorial session we'll be covering week 12's contents, which is basically a bit more about structures, which was continued from last week, and we are also going to look at how to open close files, a few questions about that, and finally pointers. So let us start this session. Okay, so first things first, we have dynamic memory allocation. So what exactly is dynamic memory allocation? Let us briefly discuss that. So till now we have seen cases where we had defined things like, okay, all right. So we had previously seen, we had defined, say, int a is equal to 50, right? Now things like this, these are statically allocated, that is, it is allocated at compile time, right? So basically when we compile the code, this there is a variable a which is allocated a memory space that is equivalent for an int, so 4 bytes, and you have the value of 50 being stored there. So whenever we define this using the static memory allocation, so this is what happens, that when we compile the program file, now the variable space is, the space for the variable is already created in the memory. But dynamic memory allocation is a bit different. So dynamic memory allocation occurs at runtime. So in compile time it will just check if there are any syntax errors, but the memory allocation part will, so the memory allocation will happen at runtime. When you finally run the code after compiling it, when you finally run it, only then your memory allocation will take place. So that is what dynamic memory allocation means. Now there are a few commands in C which you can use for doing dynamic memory allocation. So they are malloc, calloc, realloc. So malloc and calloc are used to define memory, I mean to define and initialize variables, and realloc, as you can see, it is used to reallocate memory. Okay, now these are the 3 functions that we will be looking at in dynamic memory allocation. Now let us look at the first question, which is related to malloc as well as pointers. So here what we do is we define a pointer. So whenever we do dynamic memory allocation, we have to define a pointer which will point to the newly allocated, to the first byte of the newly allocated memory. So here that is what we do. We define a pointer ptr which is of type int. So it is a pointer of integer type. It's a pointer of integer type, and we are using malloc, and malloc what? It is 5 times the size of int. So basically if the size of int is 4, then we are saying 20 bytes of space. We need 20 bytes of space for this particular pointer variable. So in the memory somewhere you will have, say this is the RAM, and somewhere in the memory you will have 20 bytes of space, and it will there will be a pointer ptr which will point to this particular memory location, in fact the first byte of that memory location. Now okay, now we have a for loop which goes from 0 to 4, because there is a condition that I needs to be less than 5, so it goes from 0 to 4, and we do is star ptr plus I is I. That means we write star ptr plus 0 is 0, star ptr plus 1 is 1 in the next iteration. So this is the first iteration, this is the second iteration, and so on. So you can see that it is kind of an array that we are defining, which is having 5 different elements. So we have basically 20 bytes of space, and that we have now divided into 5 different integer spaces, and we are saving the data 0, 1, 2, 3, 4 and 5. So this will continue till which iteration? Till there will be 5 iterations, right? I is equal to 0, so let me write that here. So here I is equal to 0, I is equal to 1, similarly I is equal to 2, 3 and 4. So here you will have ptr plus 2, 2 will be saved, and ptr plus 3, you have 3 being stored, and ptr plus 4, 4 will be stored. So basically you have this you have an array, but it is a dynamically allocated array. So you have 0, 1, 2, 3, 4. So this is what has been stored in this memory space that has been allocated to you. Now your pointer ptr is actually, like I said, it's pointing to the first element, right? The first byte, it is pointing to the first byte, to the first element. So now you are printing a series of things using ptr and the pre-increment and post-increment operators. So can you try to solve this? What the answer will be? Now I can give you a hint that the pre and post increment operators have a higher precedence than the dereferencing operator, which is this star operator. So just try to figure it out. So let's see. So like I said, the post and pre-increment operators have higher precedence than, okay, let me write it in a different way. So you have this plus plus and minus minus operators, which is post increment and pre-increment operators, and you have the star operator. So this is the order of precedence. Okay, now that means that you have first the plus plus operation, that is the post increment or the pre increment, will be implemented, and then the star operation will occur. Okay, so let's see what exactly happens. So the first thing is star ptr plus plus. So as I said, ptr plus plus will be executed first for this one, and then you will have star ptr. So ptr plus plus, it's a post increment operation. So as you remember, for post increment operation, the value remains unchanged until, the return value is the same as the original value, although internally it would have changed the value, but the return value from a post increment is the same as the original value. So ptr is at 0 when ptr plus plus is executed, and then you do a star ptr. So ptr 0 is printed, and then ptr is changed from 0 to 1. So it goes from so it is at 0, it prints 0, ptr plus plus, it still prints a 0, and then it moves to 1. So this basically what happens is, it does a ptr plus plus, but because it's post increment, it does not increase immediately. Then it does a star ptr, which gives you the value at that particular location, which is still 0, and then it actually does the increment, which is the plus plus operation, and it goes to ptr is 1. So now it points to PTR of 1, and you have 0 being printed first. So you have 0 is the first output. Now in the second part we have star PTR, but it is enclosed in parenthesis. So anything within the parenthesis has a higher higher precedence than anything that is not in the parenthesis. So here the star PTR will have a the star PTR will be executed first, which is 1. I mean the location at the current memory location that this PTR is pointing towards. So the value at that location is 1. So star PTR basically will return you that value, and you are doing a plus plus, so a post increment. So you will have 1 getting printed, but after 1 is printed the value of this will change to 2. So currently you have something like this, and PTR is pointing currently to this. Okay, now next in the next line you just start printing star PTR. So star PTR is still pointing, the pointer PTR is still pointing to the second element, that is now the value has become 2. So that is what will be printed, straightforward. It will be printed, 2 will be printed, right? Now we go to, in the next statement it is a star plus plus PTR. So as I said earlier, the pre-increment operation has a higher precedence over the dereferencing operation. So first this will do a star plus plus a plus plus PTR and then star PTR. Okay, so this technically is plus plus PTR and then star PTR. So when you do a plus plus PTR, basically we go from, it is currently pointing to this element, it will go to the next element. So it will stop pointing here, it will just a moment. Yeah, it was pointing here, it goes and points. So earlier it was pointing here, but now when you do plus plus PTR, it will go and point to this, right, the next element, and then you do a star PTR. That means it will return the value which the current PTR is pointing to. So first it moved on to the next element, and then it returns you the value. So you will have again 2 being printed here for this statement. Then the last print statement, what it does is plus plus star PTR. So doesn't matter how we write it, it is still, it will do the plus plus first. So this will still do plus plus PTR and then star PTR. Okay, so if it does plus plus PTR, that means it will move on to the next element. So instead of pointing to the third element, it will now point to the fourth element. Okay, and then it is doing a star PTR, which means it gives you the value. So and the value at that point is 3. So this will be your answer. Is that clear to everyone how this the star operation and the post increment and pre increment operations are interrelated? I mean the precedence, how it works for these operators. So basically, unless you have a parenthesis or something, for all the other steps, wherever you have both the star operator, which is the dereferencing operator, and the post increment or pre increment operator, the post increment or pre increment will occur first, and then the dereferencing operation will happen. So that is what you just need to keep in mind. Okay, all right, now let's move on to the next question. So our next question is okay, it has asked us to assume that the size of int is 4. That means each int carries 4 bytes, and we have defined a pointer star PTR, and we are allocating that pointer using malloc to size of int into 4. So basically we are allocating 16 bytes of memory to this pointer PTR. Okay, and then we are using realloc to to allocate how many bytes, size of into 2, size of int into 2, which means 8 bytes of memory to pointer ptr. So what exactly, so how many bytes, the question asks that how many bytes will the program allocate to ptr. Okay, so this happens during runtime. So first you have this star. So star ptr, however, is initialized in compile time, but the allocation of the memory to the pointer is occurring at runtime. So first we use malloc. We allocated 16 bytes of memory, but then in the next step itself we reallocate it and give it 8 bytes of memory. So basically what happens, 8 bytes of memory is freed from step from this line, the malloc line, to the realloc line. 8 bytes of memory is freed. Okay, so finally the program is allocating 8 bytes of memory to the pointer ptr. So here the answer will be 8. Okay, so realloc function, the realloc function is used to reallocate memory if you want to reuse a certain memory location. Say you needed it for an array, now you don't need it anymore, and you need it for you want to define some other array which is of different size, then you can use this realloc function to define to increase or decrease the size of the memory location, and to also change its to change the size of the memory location, you can use it. Yes, does anyone have any questions?
No, sir.
Okay. Okay, if that is clear, then we'll just go on to the next question. Before that, let me just see if you have been told about the calloc function. Okay, so there is also a function called calloc. So it is similar to malloc, but the format is a little bit different. So it's like this. So malloc is like this, right? So you have a pointer of some data type, the data type that you want. So this is going to be a data type star, that means a pointer. So this is the syntax for malloc, but in calloc it's a bit different, that you specify the number of blocks or number of memory blocks and size of each block, and similarly you will have data type pointer here. Okay, so calloc is a little bit different than malloc. Why? Two things. The first is, in malloc you just give the total size of whatever memory location you need, but in calloc it is allocated in a block sense, so more of kind of a contiguous kind of a approach to allocation. So you specify the number of memory blocks. For example, if I wanted to do the same thing using calloc, I would have written ptr is int star, sorry, let me rewrite that. Ptr is equal to int star calloc. You need 4 int, so I'll write 4 and size of int. So this is what I would have written if I wanted it for calloc. So I need 4 memory blocks, each of the size of int. So I write it like this. And the special thing about calloc is that it automatically initializes the memory to 0. So this initializes the value to 0. Okay, if I write this and I go to the memory location and see the value is already 0, but in the case of malloc it should be a garbage value, but in the case of calloc it is initialized to 0, and that is why the calloc function takes a bit more time than the malloc function, because it initializes the value of the memory locations or the memory blocks. For that reason, the calloc function takes a bit more time for allocating the data than the malloc function. But the important thing is it initializes the value to 0. Okay. Alright, so those are the three functions from dynamic memory allocation that are going to be important for you. So let us go and look at structures. So we covered structures in the previous week as well, so now we can just, try to go and revisit this. So structure is kind of a group of in a structure in C you can define different members, and the members can be of different data types, and all of those together they form the structure. Now let us see an example. So here for the first question we have a structure which is the structure name is XYZ and int a, this is the member of the structure. There is a member of the structure XYZ, right? And as you can see it has only one member which is a, and it is a variable of data type int. So if you want to access that variable you write xyz dot a. So then you access the member of that is how you access the member of the structure. Now after this, once this is the structure definition, this line is the structure definition. Now once we have defined the structure, we are defining a structure data type. So we have now a structure data type which is XYZ. So it's a struct XYZ structure, and we have defined it as a data type which contains a member which is int, one int member. Now we define a variable, a structure variable of the type struct XYZ, and we name the variable as obj1, and we give the value of its neighbor. So this is we are initializing, we are defining and initializing a structure variable of type struct XYZ. Okay, so we are defining a structure variable which is obj1 of type struct XYZ, and we are initializing the value of its member to be 11. So now obj.1 is 11. Now next what we are doing is we are defining another structure variable which is obj2, and we are equating it to obj1. So this is the advantage of structures, that is why structures are pretty handy in this case. So we can directly just do the equating part in structures. So we defined a new structure variable, and we equated it to the previous structure variable that we had. So now if we try to print obj2.a, so what do you think should be the output here? So obj2.a, basically when you do this operation you are saying that obj2.a is equal to obj1.a. This is what this line means, and obj1.a is 11. That is what we have initialized it to. Now if we write this, then obj2.a is 11, right? So this is 11, so obj2.a is also 11. Now the first output here is 11. Okay, now we set obj2.a to 101. Okay, so we set obj2, which is the obj2 structure variable, we set its member a to be 101, and we try to print obj1.a and obj2.a. So when we do that, we see that we will get obj1.a still 11, right, and obj2.a, what is it? It's 101, right? So 101. So here the answer is option B. So changing, even if we have equated obj2 to obj1, it does not mean that if we change the members of obj2 it will affect the members of obj1. It will not. It will not affect. So this is just a I mean, it did its operation is over. There is no more relation between obj2 and obj1. So once this third line is over, there is no more relation between obj2 and obj1. So any more changes we do in obj2 does not affect obj1, and any changes we do in obj1 does not affect obj2. Okay, so here that is what we did. We changed the member of obj2 to 101, but it did not change the member of obj1. Okay, so that is why our answer is 1 1. The first printed 11, this printed 11, this printed again 11, and this printed 101. So that is why answer is B. Okay, is that clear? The second question is pretty similar in nature. So we are again defining a structure of type struct xyz with a member which is A. So struct xyz with member which is A. Right, now we are defining a structure object. So obj1 dot A is 1. That is what we have initialized it to. Now obj2 dot A, we are saying that it's equal to obj1 dot A. We print obj2 dot A, that is what? That is 1, right? Then we set obj2 dot A is 100. So obj2 dot A is 100 now, and we are printing obj1 dot A, which is still 1, right? And then obj2 dot A, which is 100, right? So 100. So answer is option A. So this is the exact same kind of problem, just different values. Is it clear? Okay, so let's look at the next question. So this is again related to structure. So we have a structure which is struct P, and it has two members. So this has two members, one integer and one character. Okay, so struct P has two members. One member is an integer and other member is a character. Now inside the main function we define, so this is a data type now, struct P. So we define a variable of the data type struct P. So and you can see from the definition of this is an array of structures. Okay, so this is an array of structures. So P1 blank braces, then we give we try to initialize the values. So how is it initialized? Let us check that. So we define this. So if you look at P1 of 0, so this is the structure. P1 of 0 is a structure. So if I say P1 of 0 of x, what is being stored there? The value of 1. P1 of 0 of y, y is the character, right? So it's actually char of 90. This is what is being stored here. Similarly, P2 of then P1 of 1 dot x stores 62, right? That is the next value. So this is P1 of 0 dot x, P1 of 0 dot y is the char of this. Then this is P1 of 1 of x, and so on. So next P1 of 1 dot y, is what? The character equivalent of 33, right? That's according to the ASCII code, the character equivalent of 33. Similarly, next we see p1 of 2 dot x is 3, right? And p1 of 2 dot y is the character equivalent of 34. So that is how the initialization of this array of structures occurs. Okay. Now what we do is we do a we define another a pointer data type, which is a pointer of the data type struct p, and we set it to p1. What exactly have we done? We have defined a pointer ptr1 which points to the first member of the first structure. So this ptr1 basically is a pointer which points to the first member of the first structure. That means it's pointing to p1 of 0 dot x right now. Okay, and then we write that int x, just an integer, int x is the size of p1 by 3. Okay, now we have defined a structure, we have defined an array of structures which has 3 structures inside it. Each structure has two members, right? Now we are doing x equal to size of p1, that is the entire array of structures, divided by 3. Okay, so basically you are asking what is the size of an average size of a structure here, and then you are equating it to, in the next step you are equating through a if condition, whether you are checking whether the x that you get from here is the same as the sum of the size of an int and the sum and char. So if that is true, then you are printing true, else you are printing false. So what should be the output here? Okay, so let's say the size of, so I'm taking this assumption that, let's say the size of int is 4 and the size of char is 1, so 4 bytes and 1 bytes respectively. Okay, now when we define this structure, how it is being defined exactly in the space. So instead of the structure being of 5 bytes, the size of the structure will actually be 8 bytes. I'll tell you why. So the way this structure is allocated is this. Okay, so we start from here. The first 4 bytes carries the value of 1, which is p of, so the first 4 bytes is p of 1 of 0 dot x, the first member. This is 4 bytes, right? Because it's an integer, it takes 4 bytes. Now the next member, which is y, the next member of this structure should just take 1 byte, but what it does is it takes 4 bytes again, but actually only this byte is being used. So only this contains p1 of 0 dot y. These 3 are just buffer, so this 3 are just buffer space. Okay, Okay, they are not being used. It's just like that. And then your next value starts from here, which is now this space, this 4 spaces have the value of p1 of 1 dot x, because it's 4 bytes, it's an integer, so it takes up 4 bytes. Then again, only this next 1 byte is being used for p1 of 1 dot y, and this next 3 are actually buffer. These are again buffer. So what I mean to say here is the size of a structure can be greater than or equal to the size, or rather sum of size of its members. Okay, so that is why this is the way that a structure has been defined in C, that the size of a structure can be greater than equal to the sum of the size of its neighbors. So here the sum of the size of its neighbors is what? This is 4, this is 1, so sum of size is 5, right? But if you do the size of a single structure, so you're dividing the entire thing by 3, that means you are asking for the average size of structure. So this will actually come out to be 8 bytes. So this entire size of p1 will be 24, not 15 but 24. Although each structure, if you just look at it, it should take only 5 bytes of space, but it will not. It will take 8 bytes of space here, because you are defining an array of structures. If you had defined only a single structure, it would have taken 5 bytes, but you are defining an array of structure, it needs to be contiguous, so it takes 8 bytes of space. Okay, now if it takes 8 bytes of space, you have the size of the structure is 8 and you are comparing it to 5, so definitely it will be false, right? Now this is how structures have been defined in C. So if you want to and you can see this is a wasteful way of doing things, because you are basically, for every structure you are wasting 3 bytes of memory here for every single structure. So you could use something which is called a union. So there is this concept called a union. It is different from structure. The only difference that it has from the structure is that it takes the size of the largest element. So if you define a union P here, which has its members int x and char y, that means it will take the size of 4, which is the largest element here, which is integer. So it will take the size of 4. And now if you want to access the element, you can only access one element at a time. You cannot access all the elements at a time. So what it does is it keeps replacing whatever value you have in the same memory location. So because it has only 4 bytes, it can store only 4 bytes. So either you save the integer or you save the character. You cannot save both at the same time. But in many cases, that kind of depending on the problem, it can be useful, where you don't need to access both things at the same time. You need to partly say you need the character for some time. You're done with the character, now you need the value, so you just go and save the value. That's all. I mean, you don't need to access the character anymore. In that case, you go for a union, because that saves you a lot of space, which is otherwise being wasted in the structure. Now another question is, when will the size of a structure be the same as the size of its members? Now if I had defined a structure which was taking 2 ints, or one int and one float, which is having the same which occupies the same number of bytes, so in both those cases you would have the size of the structure to be 8, and the sum of size of its neighbors as well to be 8. So in that case you would have the size of the structure being the same as the size of sum of the size of its members. However, in this case you can see that the size of the structure is actually greater than the sum of the size of its members, because the members are consuming or are requiring different amounts of space in the memory. So this is kind of very counterintuitive, and you should do well to remember that the size of the structure can be greater than or equal to the sum of the size of its members. Okay. Now, if that is clear, then we can go to the next question. Look at the next question. So we have a character array here, which is storing all the characters from A to H. Then we define a pointer. We set it to H. That means it points to the first element, that is the character A. So this pointer P points to the first element A, and then we do a plus plus P. So what happens? So when we do a plus plus P, that is a post increment of P. P goes from pointing to from the first element to the second element, right? That is what this plus plus P means. So P now points to the second element. Okay, just a moment. So P was pointing here, but after this step, P points here. Okay, so P now points to the second element, which is containing the character B. Now we are writing a while condition, that while star P is not equal to the character E, keep on printing star P plus plus. Okay. Now the first, let's check its iteration wise. So in the first iteration, what happens in the first iteration? It checks that star P, what is star P? Star P is currently B, is not equal to E. This is true, right? P is not, these two characters are not the same, so it is true. So what does it print? It prints star P plus plus. So it's a post increment. So the post increment occurs first because it has a higher precedence than the dereferencing. So we do a P plus plus, right, and then we do a star P, but this is a post increment, so the value has not increased yet before the star P has been carried out. So after the star P is carried out, the value P is actually increased. So we are still at B. Okay, we are still at B. We are still pointing at B, and we are saying star P. Okay, so the first output that we have is B. Alright, and then it goes and it points to, and then the star PP and then the P plus plus happens, and then P points to the character C, right, because P plus plus is a post increment. Now the first iteration is over, so now we go for the second iteration. Now in the second iteration, what happens? We are pointing to C, right? We check whether it's equal to the character E. No, so this condition is still true. So again we do P plus plus and star P, post increment. So we'll look at the increment later. Star P, so what is star P currently? It's C, right? So it is C, and then after printing C, you have what do you get? You have P plus plus. Now P points to the character D. Okay, now third iteration. In the third iteration, what happens? We check if D is not equal to the character E, so which is true. So again you have P plus plus and then star P. So P plus plus post increment occurs later. So star P is D right now, and then P plus plus happens, and P is now pointing to E. So in the fourth iteration, next we look at the fourth iteration. In the fourth iteration, what happens? We check the character P is pointing to character E right now, and we check if it is not equal to the character key, which is false. So the loop will stop here. Okay, so we have output B, C and D. Is that clear how this came out to be? This is again related to the precedence between the post increment operator and the dereferencing operator that we discussed in the first question that we discussed today. Okay, alright, so I hope this is clear. If it is, then we'll go on to the next question. So this is more or less theory. Let us see the right hand side question first. So select the correct statement about structures in C. So the options are: it is wrong to define an empty structure, member variables can be added to the structure even after its first definition, and there is no use of defining an empty structure, and none of the above. These are the options. So let's look at the first option. So it is wrong to define an empty structure. Not really. We can define an empty structure. So in this problem we are defining an empty structure. It doesn't matter. Now the second option is member variables can be added to the structure even after its first definition. So we have defined a structure like this, but we can still add member variables to the structure. So yes, that is true, and that is why it is not wrong to define an empty structure. So if you define an empty structure, you can still be able to add member variables to the structure even after its first definition. Doesn't matter if you have defined an empty structure before, you can keep adding member variables anytime. So that is why it is okay to define empty structures and add member variables as and when required. So the correct statement about structures is that member variables can be added to the structure even after the first definition of the structure. Okay. Now a theory question about files, how files are being accessed. So for accessing files, you have to write this keyword file all in capital and define a pointer. Here it is fp, and this fp you write it as f, and you write f open, which is this f open is used to open and access a file in mode. This is the mode. So R basically means a reading mode, but you can use different modes as well. So this is W stands for writing mode. If you want to write into a file, this is how you have to write. Okay, and this is the name of the file. This is the name of the file, and this is the mode that you want. So it can be a reading mode, it can be a writing mode. You can append to the file. Append meaning that you already have some data on the file and you want to add to the end of that data. So you open the file in appending mode so that you can add to the data that is already present in the file. So there are different ways to do that. Now here the question asks apart from this is just f open. Now you can also you can do a f close to close the file, and it is necessary. It's not necessary at the end of the code. If you don't close the file, then anyway when the code stops executing, the file will be closed. But it is good practice to always close the file. If you have opened a file, it is always good practice to close the file after you are done with it. Okay, so the question here asks, what does fp point to in the program? So when you define a file pointer, here fp, now what does it point to? Does it point to the first character of the file? Does it point to the name of the file? Does it point to the last character of the file? Or does it point to a structure which contains a character pointer which points to the first character of the file? So here, as you can see, the there is only one option which is complex enough. So that is the answer here. So when you write this file command in capital and you define the pointer, what it does is it defines a pointer, it defines a structure. So this is everything, all of this is happening internally. It defines a structure. This structure contains a character, rather I would say with a character pointer as member. Okay, so it defines a structure which has a character pointer as its member, and this character pointer, this points to the first character of the file. Okay, so the character point, so it defines a structure, and this structure has a member which is a character pointer, and this character pointer, it points to the first character of the file. So this is how the file has been defined in C. Why has it not been defined just as a simple character pointer pointing to the first element of the file? Why not? There is a reason for that, why we have defined it through a structure. The reason is that if we define a structure, we are able to define streams for the file, and it is a bit more complicated than, and it is actually not in the scope of this particular course. That if you the structures here can also be used as a buffer space, as members can continually be added. So the space occupied by the structures can be changed mid program. So that means the structure is a flexible memory location. Now a file, as you keep on writing to the file and so on, it needs to the file does not blow up, right? And the structure can take all that data. And also for a structure, you are able to define input and output streams, which is something that we will not be discussing. So the only thing that you need to know is the input and output streams are used to input data and output data to and from the file respectively. So structures can be used for that purpose, and that is the reason why the file management in C has been defined, internally defines a structure which contains this character pointer, and this character pointer, which is the member of the structure, it points to the first character of the file. But as far as we are concerned, we can directly, once we open the file, we can directly, if we print fp, that means it will print the first character of the file. If we print star fp, then it will print the first character of the file. Okay, because that is how it has been planned. This entire structure that has been defined and the character pointer and everything is internally, it is internal to the compiler. So as a user, we don't need to really worry about that. Okay, now this is all that I had for this particular session. So in the next session, we have already covered everything till week 12, and we still have one tutorial class remaining. So in the next session, I'll be solving any doubts that you have, and also I will solve a few questions from the assignments, from this year's assignments, from each of the assignments that we have had so far, which is up till week 12. I'll solve a few questions from the assignments, and yeah, and that is more or less what we will do in the next tutorial class. So the next tutorial class will be on Saturday from 5 to 7 p.m. Okay, instead of the usual Tuesday 7 to 9 slot, we have preponed it. I think you will get a mail regarding that. It will be on Saturday, on this Saturday, on this upcoming Saturday from 5 to 7 p.m. Okay. So if there are any doubts regarding the material that we have covered today, then you can just write it in the chat, or you can unmute and ask, or we can end the class here. Okay, then thank you for joining. So I'm ending the class here. Meet you again on Saturday, 5 to 7 p.m.